So, hope everyone's having fun with the homework. I hear fun in the audience. Doubting the truth of statements, but they're true. Anyway, there will be office hours this afternoon, which reminds me, next week, Anupam and I will be trading office hours because I have a doctor's appointment on the road schedule. So anyway, but there will be regular office hours next week with different people. All right, so last time we began a discussion that we're going to continue sort of through fall break, and talking about quantum coherence and matter. So, you know, one of the basic contexts here is the famous two-level atom. Of course, no atom has exactly two levels, but we talk about that, we use that language all the time when we're talking about near-resonant phenomena, where we are driving the system with some coherent electromagnetic field, like a microwave or an optical field, where the frequency of the light is tuned close to a resonance. And when that is the case, we call it a two-level atom. And of course, you know, in quantum mechanics, we can have a situation where we have a superposition of those energy levels, and that superposition can be, as we will see, driven when can be created when we drive the system close to resonance. It's a different picture than, you know, you think about when you learn about in your first modern physics course, or as a laser physicist, where you think about quantum jumps between absorption. It goes from here to here, or it goes from here to here, as opposed to there's a Schrodinger equation. How do those pictures connect to one another? And when should we think about the system in terms of quantum jumps, and when should we think about it in terms of kind of a continuous evolution under the Schrodinger equation? That's going to be one of the themes we're going to explore over time. Okay. Right. So to get to, in some sense, to understand the distinction between quantum coherence and classical, we're quickly reviewing a very basic picture of thinking about atomic response as our basic element of matter. So we're mostly going to talk about atoms as opposed to solid state materials. Okay? Because they're simpler to deal with, and I know something about them. Right. So the simple picture here is we think about an electron bound on a spring, and the motion of that electron is then driven by some external electromagnetic field dominated by the electric force that acts on the electron. That's our basic Newton's equation, which has a restoring force, which is treated as a linear restoring force. This is why we call it linear response. And then some phenomenological damping. We're going to come back to that question about where this gamma comes from in just a moment. Right, so when we did that, we can then solve in steady state for the response, and in particular, we can look at the induced dipole moment. And because we have a linear restoring force, this induced dipole moment is linearly proportional to the applied electric field, and that proportionality constant we call the polarizability. And it's in this formalism treated as a complex number with a real and imaginary part. And excuse my horribleness of my handwriting there. Let me write that a little bit has, in the limit that the detuning and the damping are very, very small compared to omega naught, we have this approximate expression, and we're near resonance for weak damping for the polarizability, which has this real and imaginary part, and sketched out these functions, these shapes that's familiar to you. Right. So the induced dipole moment then has a component that is in phase and in quadrature, 90 degrees out of phase with the driving field, with proportionality constants that are related to the real and imaginary part of the polarizability. And we saw one way we understood what these different pieces were by just looking at how, in a simple model of wave propagation through a gas of such Lorentz oscillators, we would get attenuation and a phase shift. The attenuation depends on the imaginary part of the polarizability, and the phase shift depends on the real part of the polarizability. And that attenuation coefficient in the intensity then can also give us an expression for the absorption cross-section in terms of the imaginary part of the polarizability and the density. This is the number density. Of Lorentz oscillators. Okay? So that's where we were. So let's continue on. So let's talk a little bit about this damping. So we have this damping rate gamma here, and from where does that arise? Well, if we're talking about something like atoms, I mean, there's lots of ways you can get relaxation or damping of the motion. You have many degrees of freedom, but atoms are a little, they're kind of isolated beasts. So there's no kind of intrinsic friction within the atom that is causing this damping. But one way we can see that we would get a kind of damping of the oscillation, if we think about a gas, of Lorentz oscillators, then, well, we could have elastic collisions between atoms. And what is that going to do? Well, you can think about, if I think about, the motion of say, some particular atom, it's going to be oscillating it. And then at some point, there might be a collision of this atom with some other atom. And what is that going to do? Well, it's going to knock the position of the electron in some way, right? And then all of a sudden, it's oscillating, and then it gets kicked again. And maybe the kick gives it, some other phase shift. And then it gets kicked at some later time. And then it starts oscillating like that. So there's going to be disruptions in the phase of oscillation. At random times. Right?
phase change actually happen instantaneously?
Well, no. I mean, of course, one would have to really get under the hood to see what is the mechanism by which that phase, the degree to which we treat this approximately as an impulse, as opposed to the physical time scale over which the collision happens. But we're assuming that that is happening extremely rapidly, that this is a kind of impulse. Okay. Now, some other atom, is, I got kicked. This should be at the same frequency. Here. And this guy gets kicked here. And then again, something happens. So this is some other member of the ensemble which has its own history of random phase kicks. Okay? And if I have an ensemble of very many of these, what is the ensemble average going to look like? Statistical average of this position as a function of time. Well, for short times, time short compared to the sort of average time between collisions, I'm going to see most of these guys will be in phase. But then, after a long time, there's a kind of randomness of what phase is relative to the other. So what I expect to see in this situation is damped oscillations. Okay. And now, I could look at a kind of kinetic theory of gas to try to get a picture of that in some simple model.
Question?
Yes, listening.
So where does the energy go?
Oh, the energy must go into the heat of the gas, right? So the gas has some thermal velocity, and the collisions are causing increased entropy, and therefore heat.
So the thing is, like if you study, if you look up the microscopic theory of DC conductivity of electron gas.
Sure.
They say some of it's due to purity spectrum, some of it's due to phonons.
Right.
And then they usually write off electron collisions because they say overall momentum is conserved. One gets slower and another one gets speeded up. Now that's not like this, because this one.
Well, this is not. This is about the center of mass motion of the atoms themselves.
Right.
So if the atoms are, you can imagine, let's say I created something with very low entropy with a well-defined momentum. The atoms start colliding with one another; they will thermalize. And so the thermalization of that of the momentum into a Maxwell-Boltzmann distribution has to be associated with energy coming from somewhere. And in this case, we're taking relative motion energy of atoms, of electrons and the nucleus, and putting that energy into the center of mass motion of the particles. And it's that's how energy must be conserved. Energy must be conserved in terms of energy going from relative motion of electron and nucleus into center of mass motion. And it's not the kind of thing that you would see in a solid state textbook, because they're not looking at gas phase. I'd like to move on. Right. So I was just going to say, let's have a simple model here that of this, which is, let's just assume, for simplicity, just to get some picture of what's going on, let's assume that I have every collision imparts a phase shift. I'll call it phi1. So it's the same phase every time, okay? And let's assume that this happens, we have a mean field free time tau naught between collisions. What this would get in a kinetic theory is we would get what's called phase diffusion. So it's kind of a random walk on the circle. The phase is randomly being kicked with a random walker that can go to the left or the right with this, and that will cause the phase to diffuse. And on a random walk, we know that the probability of seeing a certain phase after a certain amount of time, given a random walk, is what? Listening? A Gaussian distribution, right? So I'm going to get some Gaussian distribution here. With some variance and a mean of 0. And how does the variance vary with time for a random walk? How does it change with time? It's proportional to time. Right? So it's proportional to time. And if this is a phase, well, it's got to be in units of the characteristic time, right? There's some characteristic time scale. And there's some proportionality constant. Let me call it, suggestively, gamma. Okay, that's just the proportionality constant right now. So now if I were to ask, what is the average position of this thing, averaged over the probability distribution? Let's look at the complex amplitude. This is the Fourier transform integrating here over phi of the probability distribution. And when you do this integral, of course, what I'm going to get is the inverse, right? Because you take the Fourier transform of this with respect to phi, the thing in the denominator goes into the numerator by the Fourier duality, and this becomes e to the minus gamma. Let's see, maybe I'm choosing my notation incorrectly. Hold on a second. Yes, I did, because really, I got that wrong in my head. Of course, what's here, from a random walk perspective, it depends on the strength of the walk. So this should be phi1 squared, right? The spread depends on the size of the walk. Gamma is equal to a combination of these guys. So this guy is going to be equal to e minus gamma over 2t. gamma is equal to the phase step over tau naught. So the rate of damping here depends on how big of a kick in phase I get in each collision, as well as the mean free time between collisions. So this is one way we would see damping in a Lorentz oscillator model. This gives rise to a line width in the absorption, as we saw, the thing that was just erased over here. That depends on the rate of collisions, and sometimes in old-fashioned laser physics, this is called pressure broadening. You turn up the pressure, and you're going to broaden the line. Why? Well, you get more collisions, and the more collisions you have, the more you can transfer energy to the system, absorb it, and therefore get a broader line width. That's called pressure broadening. Yes, sir?
Could you also take it into, or think about it in terms of coherence length?
Yeah, we're going to relate that absolutely in a little bit to the coherence length of the emitted light. Right now we're talking about the matter. When we talk about coherence length, we're usually talking about the field. We'll come back to that a little later. But they are intimately related, absolutely. All right, now let's suppose that I have a very, very, very cold gas of atoms. A gas that is laser cooled to 10 microkelvins. And it's pretty dilute in sitting there collected out of a magneto-optic trap with about 10 to the 10th atoms per cubic centimeter. That's like nothing. And there's like no way one atom's going to collide with one another. So, in that circumstance, if I were to think about this from a classical point of view, would the oscillations go on forever? No. There is always a fundamental natural line width. So the natural line width is what we call also the radiated line width. So the radiated line width of this system, well, let's think about this again from the point of view of the Lorentz oscillator. I have this electron, bless you, bound to the nucleus. It's being driven by the applied field, and it's oscillating up and down due to the force of the electric field, say that's polarized in this direction. Okay. This oscillating electron, of course, as we discussed at the very end of last lecture, will radiate. It will radiate electric dipole radiation, right? And we'll have a dipole radiation pattern. Some of the field goes here, depending we have this pattern of radiation, right? We're all familiar with that. Question. What is the rate at which such an oscillating charge radiates power? Radiates energy. So the power radiated, that is the amount of energy per unit time that is radiated by such a oscillating charge. The Poynting vector is about the flux of energy, the energy per unit, time per unit area. If I integrate over all 4 pi, for the specific case of a charge that is going up and down, is oscillating, the Larmor formula for the radiated power, which is what? Those of you who took 511, or 406? Alejandro! First question, how does it depend on the acceleration? Square. Okay, good. We got that. So it depends on the square of the acceleration, and that's all I really care. And the rest of it is, there's a 2, there's a 3. I remember that because then there's a C cubed, see, 2 and 3. And then it's the electron charge. Okay. So, that's the Larmor formula, right? Now, there may be a 1 over 4 pi epsilon naught, but you know, what's a 4 pi epsilon naught amongst vague friends? Okay. So that's the amount of energy radiated per unit time by this oscillating charge. Where did that energy come from? Come from the kinetic energy of the motion of the charge. So if the electromagnetic field is carrying off this amount of energy, the motion of the electron must be damped. That's what we call radiative damping. Okay. Now, what is the rate of that? That's a complicated story. So what we are looking for in some sense here is the back action that the field of the electron has on itself. And that has a long and storied history in physics, the story of radiation reaction. So we can say, try to get it, I'm just going to quickly go through, you know, whatever, one of the last chapters in Jackson where this is discussed, or maybe it's in Griffiths, I don't even remember. But let's just quickly talk about it. So the idea here is I say, all right, look, Newton says that the rate of change of momentum has to be the force that's acting on the system. And this force could be whatever the external force is that's being applied, plus the radiation reaction force. The force on the charge by its own electric field. Okay? So we want to calculate what that is. Remind myself of some things. Right. Oh yeah, okay, I'll come back to that. So, the way we're going to do this is we're going to say that the work done by radiation reaction equals the energy carried away by dipole radiation. Okay. So, the work done is equal to the force through the displacement, you know, 161 physics still matters. That's the work done by the radiation reaction force on the particle, if I say over some time interval, say from time t1 to t2. And that has got to be equal to the decrease in energy which I'll write, bless you, as the acceleration as v dot. With itself. Everyone clear on that? So now, to do this integral, we do the famous integration by parts. And everyone knows how to do integration by parts in their head, without the stupid u, v, d, v, du, the thing we learned in calibration. What integration by parts means is you take the derivative on one thing and you throw it onto the other and put a minus sign. So this is d by dt of d dot into, and I take one of these derivatives and I throw it onto that side. And then I have the so-called surface term. The surface term is just the thing without the evaluated at the endpoints, which is the surface. Integration by parts in your head. All right? So, now for this particular, we can look at a specific case where we might consider a situation where, oh, we're looking at a time interval either where the particle starts at rest and ends at rest. That's one case we might be interested in which case the surface term is 0 because v is 0. Or we have a situation in which the system is periodic in motion. And if it's periodic, then this is the same at both endpoints. Okay? So for either of those cases, the surface term is 0. For periodic, and let's focus on that particular case of periodic motion, because that's what we're most interested in. Okay.
Sorry,
I'm listening.
where you have f dot b and then you end up with b dot.
On the left-hand side here is the work done by the radiation reaction force. On the right-hand side is the energy carried off by normal radiation. And normal radiation, well, I wrote it many different ways. I have a squared, I have this. I have e squared over c cubed d dot dotted into d dot. That's what I did. Yeah. Yes, sir.
Is that first term of the integration by parts dv dot by dt?
Sorry, yeah, there's the square, I'm sorry, that was my mistake, got T2, I got initially. T.
I mean, in other words, it's d squared v by dt.
Oh, yes, it's the second derivative. I'm putting one of these derivatives onto that. Yes, thank you. Sorry about that. Yeah, indeed. Correct. Good. So if this is true for any v, then we have an expression here for the radiative force. It's 2/3 e squared over c cubed times the second derivative, which is the third derivative of the position. So, the so-called Abraham-Lorentz equation is that the motion of the electron in this particular case is the external force plus this radiative force. How many people have ever seen this equation before, just out of curiosity? It's not something that's taught very much these days in the now, yes, sir?
Where we pick up the extra derivative? Okay, second derivative.
Because I took the integration of by parts did that. Yeah. Now, this equation is pathological. It has completely unphysical solutions. For example, I can set the force external to be 0, and a solution to this equation is equal to whatever the initial acceleration is at time equals 0, e to the 2/3 t over something I'm going to call tau rad, or tau rad, which I'll explain in a moment. I forgot to go over our scales, is equal to e squared over mc cubed. Now that solution is acausal. It says all of a sudden the system, even in the absent force, is going to start exponentially accelerating in an acausal manner. So it's saying that there's something wrong in the classical physics that describes radiation reaction. And in fact, there is no way to rectify that within classical electrodynamics. It really takes the quantum theory of the electromagnetic field, quantum electrodynamics, together with charge to really get this right. Okay. However, we can get an approximate solution that is useful in the following circumstances. So let me back off now and talk about scales of the problem. As I emphasized, I think, at least once, but I always emphasize, really the first thing you should do when you see a new problem is ask what are the relevant scales in the problem, given the constants that we have. So in this case, we have the charging electron, we have the mass of the electron, and we have the speed of light. So what can we do with that? Well, I can ask what's the characteristic length scale that I can make out of these constants. Now, you might throw in epsilon naught if you care to, but I don't care to. And the way that I would think about a length is, well, I have an energy scale. MC squared is an energy. And I know that E squared over some characteristic length is an energy, because that's the potential energy of the system. And that characteristic length, E squared over mc, is known as the classical electron radius. This was a picture that Lorentz had of the electron as a ball of charge, and that you can think about the rest mass of the energy as somehow being associated with the potential energy that it would take to squish one electron charge E into a ball of radius RC. Okay. That radius is equal to something super tiny, and I don't remember what it is. Oh yeah, that's right, it's a femto. Now I can think about a characteristic time scale, which I'll call the radiated time scale, which is the time it takes light to travel across that ball charge. Right? And that time is E squared over mc cubed, and that time is microscopically tiny. It's 6.67 times 10 to the minus 24 seconds. Is that right? Yeah. Oh, so it says my notes, if it's right. Okay. So.
Doesn't seem consistent with our speed.
You don't think so?
The C is 3 times something.
2.8 over 3.
Yeah, so I got 10 to minus 8. Yeah, seems wrong, doesn't it? Probably, it's on the order of, I'll say, divided by 10 to the 8. Yeah. Squiggle for when all else fails. The number doesn't really matter, I don't really care. It's not the point. The point is the following. So, if the force of that is applied externally is such that the system accelerates not very much over this time scale. So the time it takes for the velocity to go from some zero to something else, there's this characteristic time scale of acceleration that depends on the external force. Then I can think about the external force as much bigger than the radiative force, and think about the radiative force as a perturbation to the system, and not on the same par. Okay? So for a weak external force, I can do this, but only treat this acceleration not as to do to both of the system, both the radiative force and the external force, but dominated by the external force. This is a perturbative expansion of this radiative force. So I just, instead of having v squared, I said, well, one of these v's is going to be due to both, the other one is just going to be dominated by the external force. So to lowest order in the radiative force, this is what I would say. And now I can do my same integration by parts, put the derivative here on that side with the minus sign, get rid of the surface terms, and in this perturbative limit, I get a manageable expression for the radiative force. And that expression is as follows. So we can look at that in the particular case. So this is equal to 2/3 that characteristic time scale df dt. Now let's look at this in the specific case where the external force was just due to the binding force of the electron to the charge. So in that case, we just got Hooke's law, and this is equal to 2/3 T rad and omega 0 squared R dot. So, if I now look at Newton's equations, the force is equal to the external force now due to the field. And then this force coming from the radiation reaction due to the binding. Then this is equal to the same kind of equation that we had before. Oh, I also have the binding force, field plus binding. So I gotta have the binding force in here. Where, what is gamma now? Well, it's equal to 2/3 squared. Or 2/3 E squared over MC cubed omega 0 squared. Yes, sir.
The units don't appear to match between the second and third things you've got set equal to each other on that second line.
This guy? Which one?
You have mass times acceleration and then acceleration.
Yeah.
I think the second equal should be like an arrow.
Oh, this one. Yeah, sorry. Sorry, yes, pardon me. Yes. Arrow, like squiggle. Thank you.
Thanks.
Yes. Right, so interestingly, if you've never seen this before, this is the classical expression for radiation damping. If I have a mass on a charge on a spring, and I let it oscillate, and I want to know what is the rate at which energy would be damped from the system in this cockamamie classical picture with radiation reaction with some sleight of hand. Oh, this is perturbation, so ignore that and put that in there, and I kind of do a little dance. I get this. And this expression is amazingly close to what you would get from quantum mechanics, as we will see a little bit later in the semester. In fact, so quantum mechanically, if I have a two-level atom with some Bohr frequency, which is the resonance frequency of this two-level atom, and I have a dipole matrix element, which is the matrix element of the position of the electron between the ground and the excited state. So this is my electric dipole matrix element. Then quantum mechanically, the rate at which an oscillator would damp, if I have oscillation between these, is known as the Einstein A coefficient, or the spontaneous emission rate. And that spontaneous emission rate is given by the following. 4/3 dipole matrix element squared over h bar omega naught cubed over c. Okay. I'll call this Qn. We'll call this classic. So the ratio of these is what? The ratio of the quantum rate of decay to the classical rate of decay is equal to the following. 2m omega naught over h bar times the matrix element of the position of the electron relative to the nucleus squared. Question: does anyone recognize this combination of h bar, m, and omega? Maybe. What about for a quantum simple harmonic oscillator? If I have a quantum simple harmonic oscillator, and I asked you, what is the characteristic length scale associated with a quantum simple harmonic oscillator? you would say h bar over m omega. Because if I say the characteristic energy scale is h bar omega, and the characteristic that has to be m omega naught squared times some characteristic length scale, then my characteristic length scale squared is equal to h bar over m omega naught. All my students from 491 remember that. So that's what we got going on here. We have a quantum length scale associated with a harmonic oscillator, and the actual length scale associated with the dipole matrix element. And this ratio is known as the oscillator strength, sometimes called F. So back in the day, even before my day, when Lorentz was doing something in the early part of the 20th century, and they were looking at, they had this model of the electron bound as to try to explain absorption line shapes. The Lorentz oscillator model worked pretty well, but they had to put a fudge factor in. And that fudge factor was called the oscillator strength. They didn't really know where it came from. But basically, we can, in large measure, explain and understand certain features of atomic gases or molecular gases or solid state in a classical electromagnetic way if we just throw in the oscillator strength. We can get the oscillator strength and we'll get the line width just right. We have to calculate the oscillator strength based on the wave functions, because of course this matrix element depends on the wave functions. Yeah?
Is there any particular significance in the factor of 2?
No, it really isn't. I mean, that's just, these are scales. They're not exact. Yeah. All right. Very good. All right. So, let's shift gears a little bit. We've talked about, we've mentioned the word now many times, quantum coherence, but we haven't been precise. So now let's get precise. To do that, I want to go back and motivate where we started our semester, thinking about interference and the double slit experiment. So we had the double slit experiment. We sent in light, which had some amplitude, and going through slit 1 and slit 2. Right? And our total field with the right propagation factors at position 1 plus position 2, and our intensity in general would be, I think about this as some kind of stochastic field and have an ensemble average in terms of the intensity through slit 1, the intensity through slit 2, and then twice the real part of E star. This way. Doesn't matter which one to put the star on. And this, of course, told me something about the interference between those. Now, thought about from the point of view of the individual particles, the photons in this case, we would write down probability amplitude, right? And think about the total probability density in terms of Born's rule. And of course, we talk about this as terms involving quantum interference. Now, if we express that probability density from the point of view of bras and Kex, of course, the probability amplitude at some position is just the state vector in the position representation, right? So, in that case, we have that, say, the probability density associated with wave function 1 is that. And this term that has to do with quantum interference involves written in the funny way that I have, because there was a particular method to my madness. Is that. And so both of these numbers can be considered as matrix elements of an operator. The operator that you may or may not have seen in your previous studies, but we'll do it pretty quickly for those of you who haven't. This operator rho, which is the outer product of the state with itself, is the density operator. And importantly, what we see is two different kinds of matrix elements here. We have the diagonal elements, in this case, in the position representation, kind of not really a matrix, of course, but nonetheless, it's the diagonal matrix element here, which has to do with the probability. In this case, the probability density. Here we have off-diagonal matrix elements. The off-diagonal matrix elements of the density operator tells me about the ability to see interference between the alternative paths, whether or not it went through path 1 or path 2. And these elements of the density matrices we call coherences, because they tell us something about the ability of the system to exhibit interference. So these off-diagonal elements, in this case in the position representation, represent psi and psi star at two different points. That has something to do with coherence, whereas the square, was a probability. Let's talk about the density operator. For the case of a basis that is discrete. So let's say I have a basis. Up to whatever the dimension of the Hilbert space is. Could be an infinite dimensional Hilbert space. I'm not too demanding. So let's look at, if we wrote the state written as a ket, we can of course always expand it as a superposition of the basis vectors. Right? The density operator is the following. It's the outer product of psi with itself. So I'll write that psi with two different sums. So these are the matrix elements of the density operator. They're like psi and psi star, but now in terms of general probability amplitudes, right? Arranged into a matrix, we call it the density matrix, and we use those terms, even if we're not talking about an actual matrix, sometimes that operator rho we call the density matrix, just because we do. So, how do I interpret the elements of the density matrix? So, the diagonal matrix elements in this case, in a particular, with respect to this basis, I guess I should call it E alpha, because I did it, represents the probability to find outcome alpha when measuring in the basis. Saying I measure in the basis is to say I measure some observable whose eigenvectors are that basis. Okay. It really doesn't matter what the eigenvectors are. The eigenvalues are irrelevant. It's the eigenvectors. Okay. The off-diagonal elements are what we call the coherences. And they tell me something about the effect of interference between alternatives. So a system which has coherences, has large off-diagonal elements of the density operator, means that there can be some experiment I do for which interference between these alternatives will manifest itself. Let's think of such an example. correction. Think about this for a minute before we see what I do. Okay, yeah. All right, let's suppose I take the state psi. Let's consider the special case. As we will for quite a bit of a simple system, which is a two-dimensional Hilbert space. Of course, this is isomorphic to spin 1/2. Okay? So, yes?
Is there any classical analogy to this operator?
You may have seen in your advanced optics Jones matrices.
Okay.
It's the same thing. It's exactly the same mathematics that talks about coherence in polarization, unpolarized states, and so forth. It's exactly the same mathematics. We'll see the relationship between those soon for those optics. All right, so we're going to take the spin 1/2 system. I can have different, I can think about bases, say eigenvectors of sigma x, sigma y, and sigma z. It's absolutely critical that you review, if you're not at your fingertips, the quantum mechanical algebra of Pauli operators, Pauli matrices, and spins. We've been using it extensively. All right? So let's, for example, so I could have an example basis. I'll take spin up along x and spin down along x. That's a basis. Or I could think about the basis of spin up along z and spin down along z. That's the standard basis. Or if you want to use quantum information, then you call it the computational basis. All right, so let's suppose I take my state psi to be spin up along x. What is the density operator is the projector onto that state. As a matrix, in Deutschian notation, when I write it as a representation, put a dot on top to say that this is representation with respect to a particular basis. Okay? So this is a basis-dependent thing. If I look at this in the x basis, what does this matrix look like? 1, 0, 0, 0. Of course, you have to decide on the order. This is the order. Okay? What about with respect to the z basis?
1, 1, 1.
Sort of. There's a root 2 in there. 1 over root 2, 1, 1, 1, 1, 1. How do we know that? Well, we know that because up along z is 1 over root 2 up along x plus down along x and down along z. No wonder these guys have to have a minus sign here. Now it makes sense. All right? You agree? Now we need to memorize these things. Yeah,
Isn't that traceless?
that's a problem, isn't it? That was a problem. So did I memorize something incorrectly here? You must be, let's think about this. So we know that this we know is true. Okay. Yeah, I'm sorry. It was right the first time.
Yes.
It was right the first time. Because this, yeah.
It should be a half insert of the one that.
Yeah. No, because this is equal, this is 1 over root 2 up along z plus down along z. And I think the outer product of this with itself.
So the factor should be 1/2, no 1 over the square root.
That's 2. Indeed. Absolutely. Okay, now we're happy. All right, so here's your question, folks. Does this system have quantum coherence in it? Well, it kind of depends what you mean. These off-diagonal matrix elements are 0. So from the point of view of some kind of measurement that I would do here, there is no interference between different alternatives in X. However, there are off-diagonal elements here, just circling this, which says that there is some interference effect associated with different alternatives in Z. Let's see how that works out. So let me just think about this from the point of view of logic. I want to know what is the probability of saying finding down along X, given that the system is prepared along, so it's a conditional probability of finding down along X, given that I prepared up along X. Okay. Of course, that should be 0, but let's see how I can understand this from the point of view of quantum interference, which will be important for our understanding of the density operator. Okay? So, let me write this. Sure, I write this the better. 1, 2, 2. Right. Okay, so the state I prepared is up along X, whose density operator is this. And according to the rule, if I want to know the probability of finding down along X, I should take the diagonal matrix element of the density operator with respect to the thing I want to know. What's the probability of finding down along X? Okay. Now, I'm going to stick in here a complete set of eigenvectors along Z. Okay. I'm going to put a resolution of the identity as a sum of projectors up along Z and down along Z, and just shove that in there. Everyone would agree I could always do that. It's just changing the basis from X to Z. And what do I get when I do that? Well, I'm going to get the terms that look like this. finding. Those are the four terms that occur by multiplying out. I'm going to have 2 in each, and shoving in this row is a projector along X. Now, what's the point? Let's look at what I have in here. This we understand as the probability of finding down along X given that the state was up along Z. And this is the probability that the state actually was in Z, right? Because I take the diagonal matrix element, and that's the probability that the state was up along Z. This over here is the probability of finding down along X given that the state was actually prepared and down along Z, times the probability that the state was actually prepared down along Z. These first two terms are classical logic. It could have been up along Z, it could have been down along Z. I didn't know. There's some conditional probability that I'll find down along X given that it actually was up along Z. And then I multiply that by the probability it was up along Z. Or it might have been down along Z. I didn't know. There's some probability that I could have found down along X given it actually was down along Z. But that's classical logic. The rest of this represents the quantum interference effects having to do with coherence that exists in the superposition of up along Z and down along Z, which is here. The system exists in a superposition of up along Z and down along Z. And because of that, I can't just think it was either up or down. I didn't know which one it was. That's a classical way of thinking. I have to think it's in a superposition of up or down. And that means that I have to add an interference term that's related to the coherence that exists as quantified by the off-diagonal elements of the density matrix. And so, when you write all of that out, what I get is a half times a half, that's each of these guys, plus a half times a half, that's each of these guys. So in the absence of quantum interference, about this probability would be a half. However, when you put in what those off-diagonal matrix elements are with the right minus sign that I've written over there, this is equal to 1 over root 2 times minus 1 over root 2 times a half plus minus 1 over root 2 times 1 over root 2 times a half, which is a quarter plus a quarter minus a quarter minus a quarter, which is 0. Now, what a long-winded way of saying the obvious thing that if I prepared it spin up along X, and I ask what's the probability of finding spin down along X, the answer should be 0. But it's an important point here that in terms of thinking about orthogonal alternatives, in this case up along Z and down along Z, I could not just argue logically, which is the first, these two terms are just classical logic for finding the outcome down X given these two alternatives, those possibilities are canceled completely due to quantum coherence. And the degree to which they are canceled depends on the strength of these off-diagonal matrix elements. If those off-diagonal matrix elements were 0, then the probability to find spin down along X would be what? It would be this, which is a half. We'll come back to that.